Seen? Okay. Okay. Good evening.
Okay, good evening. I'd like to thank you for this invitation to this IEEE presentation. Without further ado, let me share. One second, just share the screen. And we should now be seeing the screen. Could I just confirm that you are seeing the screen? Anybody?
Yes, I can see it.
Great.
Good evening.
Wonderful. Okay, so my presentation is on error control codes. I work at the University of the West Indies. Forgive my dog, please. When you don't want the dog to make any noise, that's exactly when it happens. Right. So that's where I am in Barbados, tiny little island there. The abstract, my main objective is to take you through the evolution of error control codes, from simple beginnings to some of the most powerful codes that have achieved essentially the promise of Shannon's channel coding theorem. So here are basically the outline of what we're going to look at: the introduction, the digital communication systems model, Shannon's promise. I will attempt to cover 68 plus years of journey within 5 minutes, look at some milestone codes that were very important as the beginnings to this journey. And then we look at 3 of the most powerful codes that we have. I will be looking at the encoding part only, not the decoding part. The encoding is easy, the decoding is a lot more involved and very mathematical. But for this presentation, at least you'll get an insight into the journey of error control codes and what lies ahead. So the communication system model that I'm looking at is a binary source. So these are the ones and zeros that you want to get across the communication system from, forgive me, from the source to the sink. Now, my assumption here is that I'm doing error control coding at the physical layer. So this is where the ones and zeros are actually put through an encoder, which will add more binary digits. So these ones and zeros that come out of here are the ones that you want to get across to here. But this encoder, which is the main objective of this presentation, is going to add binary digits. So more binary digits will come out of here. Then at the physical layer, it may enter a modulator. In this case, it's a QPSK modulator. The waveforms travel across the channel into a demodulator. The decoding happens, and we come back at the sink. Now, the name of the game with error control coding is to try and get the probability of an error in a binary digit here to be as low as possible. And if it's somewhere around about 1 × 10⁻⁵, then that is just barely acceptable. And with the error control codes that we have now and that I will show you today, we can bring that down to about 10⁻17. Imagine that, 1 × 10⁻17. That's the kind of power we're talking about between encoding and decoding. Whenever you see a plus sign in this presentation, it truly is, it's not algebraic addition, it is XOR addition. So 0 and a 0 make a 0, a 0 and a 1 make a 1, 1 and a 0 is 1, and 1 and 1 make a 0. This is the XOR or the modulo 2 operation. So let's begin with Shannon's promise. 1947. The red curve is Shannon's promise. And what it's basically saying is that if the number of binary digits per second that you wish to send is greater than the channel capacity in bits per second, error-free communication is not possible. On the other hand, if RB is less than C, error control coding is possible, and you can bring down the probability of an error in a binary digit to be essentially as small as you want it to be. Now, there are many dots and places along here, but let me focus on a very simple case. They take a look at uncoded binary phase shift keying, the most famous modulation scheme where you're sending binary ones and zeros. On the horizontal scale, you have signal to noise ratio. So this would be 9.6 dBs, and it's giving a probability of an error of about 10 to the minus 5. All of these points are at a bit error rate of 10 to the minus 5. Our objective is to get this blue dot to move along to the red curve. No matter where you are, you want to be on the red curve. That this is the promise, that this is actually possible. Shannon didn't say how, but he proved theoretically through information theory that it is possible to lie on this red curve. So for example, if you're using a modulation scheme in which M is 16, in other words, there are 16 constellation points, and you are sending a waveform that is representing 4 binary digits, as opposed to here where a waveform is representing 2 binary digits, it is more bandwidth efficient. And so it is higher up along this vertical scale. And the ideal would be to bring this point all the way to the red curve. Now, 1940s, 1950s, 60s, what we've been doing is we've been using a rate half code. So for every 1 binary digit that enters the encoder, 2 come out. And what you find is that the bandwidth requirement goes up, so that the bandwidth efficiency, if this number goes up, then the ratio comes down, and we end up somewhere here. So if I'm going to show you this, I'll show you hard decision Viterbi decoding, and then soft decision. And this is basically showing you the early stages of error control coding. These are the days when NASA was sending up space probes, the Galileo space probe. We were using exactly this type of code. And what was happening was that this dot would come down here, more bandwidth required. And with the k equal to 7 NASA code, we were sitting somewhere around about here. And people realized very quickly that we're very far away from the promise of Shannon. And this journey from here to here is about 60 odd years. Believe it or not, it took about 60 years to move this point down to here. And let's take a look at that. Some of the points that I've made here is that the channel bandwidth, this is the capital B, and the transmitted power, which is this ratio of EB upon N naught. N naught is the single-sided noise power spectral density. EB is the energy per binary digit. They're the 2 main precious resources for a communication system. So this is the big picture, and TCM here is trellis-coded modulation, which I will mention briefly, and you can see its journey along the path. Turbo codes we will look at, one of the most powerful codes, and this was a revolution. We moved from here to here, and that was a huge step. As soon as turbo codes came out, we then managed to creep along here. So let's look at that journey. The 68 plus years of journey. So repetition codes are centuries old. Let me give you a very simple example. If you wish to send a binary digit 1, you could replicate it 3 times. So that instead of sending a binary digit 1, you could send it 3 times, 1, 1, 1. Then at the receiving end, you would use majority logic to decide whether a 0 or a 1 was sent. So that if you received 2 zeros and a single binary digit 1, you would say, well, I've got more zeros than a 1, so it must have been a binary digit 0. So repetition of binary digits, letters, symbols, anything from a finite set of symbols is centuries old. And that error control coding took formal mathematical form in the 1940s. Hamming single error correcting code, which we will look at, and then Go layer 3 error correcting code. We won't look at this, the most important one being this. In the 1950s, the construction of 2 more important block codes. What are block codes? Block codes are where a certain block of binary digits enter and a certain block of binary digits exit. So for example, 4 could enter and 7 could exit, or 3 come in and 6 could come out, as an example. So the 1950s, about 10 years later, we evolved the mathematics of block codes to the point where BCH codes were created, non-binary codes, and non-binary Reed-Solomon codes, again, block codes. 1960s was a revolution. People were resigned to the fact that we will never achieve Shannon's promise, and block codes is the only way. Whatever comes in, you have to then add binary digits and something must come out. It was in, out, in, out. Convolutional codes broke that rule. It was continuous encoding. So these are non-block error correcting codes. The Viterbi, Andrew Viterbi, his algorithm was the most famous. Of the two well-knowns, Viterbi was the most famous. And because of their performance and because of their error control coding performance and encoding simplicity and the ability to add soft decision, which in this presentation I don't have time to get into, they became the most widely used type of error control code. In fact, they were used by NASA for space probes. They were used for hardware. They were used for your CD player. The ones and zeros were encoded using convolutional codes and decoded using the Viterbi algorithm in a simple CD player that is in your computer. So convolutional codes very quickly overpowered block codes. Now, on the other side of the coin, in 1960s, something wonderful happened. Gallagher, a PhD student at MIT, he came up with codes which were block codes, not convolutional codes, block codes, Gallagher codes as he called them. And they were largely ignored because of the processing power that was not available in the 1960s. And what is truly amazing is that they were later rediscovered in 1997. Just look at the gap. Just look at that, 1960s to 1997 as low density parity check codes. Incredibly powerful. They've made their way into the 5G standard, and they are beautiful, simple and beautiful, and work very well. And our PhD student discovered it in 1960, and we didn't even realize that Shannon's promise had been discovered in the 1960s. So another 40 years went by, another 30 years went by. 1970s, people looked at concatenated coding schemes where you had an inner convolutional code. You sort of combined the convolutional code with block codes, and the most famous being the inner Reed-Solomon code in combination with convolutional codes. And you can look into that. And they were used for space systems as well in the 1970s. 1974 was a breakthrough. Not realized until much later on, but 1974 was a breakthrough with the map algorithm, as it's known, maximum a posteriori algorithm by Bahal et al., sometimes called the BCJR algorithm. And what it did was, unlike the Viterbi algorithm, this minimizes the probability of an error. There's a slight modification to the algorithm, more probabilistic, and in 1974 onwards it was ignored. We'll come back to that. 1980s, Ungerbock again looked at concatenated coding schemes, but he said, why are we separating, right? Why are we separating the operation of this and this? Why don't we combine the two? So what Ungerbock looked at was coded modulation, a generalized form of a concatenated code where the modulation and the mapping scheme, the encoder, are fused into one. And at the decoder, you use the Viterbi algorithm. It's an intertwined combination of the encoding and modulation scheme and the demodulator and the decoder. So this was responsible for the 56K modem, the modem that, if you're old enough to remember using the phone lines, people were amazed by TCM codes, trellis-coded modulation codes, as they were referred to. And Ungerbock was heavily praised, and we thought we'd achieved a wonderful error control coding scheme. But of course, a 56K modem cannot handle the video over a phone line. Now, look at that gap. just look at this gap from 1980 to 1993. Just look at this. Look at that gap. People had been searching and searching and were stuck with this. It wasn't until the French researchers took the map algorithm. Okay, so they took the map algorithm from 1974 and they achieved near optimum performance with turbo coding scheme based on the map algorithm. So they were very close to the Shannon's curve, and everybody thought, we've achieved it, we've done this. Turbo codes were initially adopted for the 3G mobile telecommunications, CDMA, digital video broadcasting, and deep space communications. Now, everybody looked at how is it and why is it that this works so beautifully? And we will look at turbo codes. And very quickly, people realized that this is iterative decoding. Okay, this is iterative decoding, which was a major breakthrough in the way in which decoding is done. Decoding up to this point was you have the message vector, you message binary digits, you put it into the encoder, out pops out a code word, and you decode the code word, and you output the message corresponding to the code word. There was no iterative process of trying to take the code word, examine it very carefully, and see which parts of it were received without much error, and use those to correct those code digits that did have error. And so iteratively, using the bits of the code word that you've received to remove errors and ultimately produce a much better decoder. We will look at that in brief. And this process of iterative decoding led people to rediscover low density parity check codes. And McKay and Neal were the ones who did it. And of course, it was originally proposed by Gallagher in 1960 and further investigated by Tanner in 1981. And what McKay and Neal did was took the two and renamed the codes as low density parity check codes, and they became block codes. So we came full circle. These are convolutional codes. This is still the operation of iterative convolution. Iterative convolution. This was block code. So block codes made a comeback. And then the icing on the cake was very recent. Polar codes invented by Professor Arikan from Turkey, Bilkent University, and they've been adopted immediately within the 5G standard along with LDPC codes, and we will certainly look at both of these. Very elegant, very beautiful. Let's take a look. Let's take a quick look. So some of the milestone codes. What is a block code? Right. So what exactly is a block code? Well, this is a generator matrix, and this is the message. These are the binary digits that will enter the encoder. So 1, 2, 3, 4 will enter, and what comes out is 1, 2, 3, 4, 5, 6, 7. So 4 enter, 7 come out. 4 enter, 7 come out of here. So how do we do it? Well, this is a generator matrix, and I won't worry about how I got these ones and zeros. What is more interesting is that I've got a sequence of ones traveling along here. And when I multiply this matrix by this matrix, a very simple block code, then you get a code word in which you recognize that this is the message bits that you wanted to send. So the advantage being is that when you decode the code word, the message, the bits that you want to extract are already embedded inside the code word. So this is a systematic code, and these are parity bits. And the way we decode it is that you take the code word. R represents the code word, which we say is the original code word, like this, plus an error vector. If you were to take the code word received and you multiply it by the transpose of the parity check matrix. Now, the parity check matrix is something that is derived from this, and its unique property is that if you multiply it by this, you get an all zero matrix. So if you take the transpose of the parity check matrix and multiply it by the code word, what actually comes out is this will actually go to zero. This will actually go to zero because of the way in which the codes, the matrices are made. So what happens is that this multiplication of the received code word with the transpose of the parity check matrix produces a syndrome. And here's an example for this seven code word block code, is that if the error vector was something like this, if the error vector was this, then this would be the syndrome. In other words, if this particular bit was flipped to a 0, that would correspond to this particular error vector. If you look at this, then this particular bit would have been flipped. Sorry, this would have been flipped. So using the syndrome, you can figure out what the error vector is and correct it. A very, very simple code. Cyclic codes came out of this very simple invention of block codes. And a cyclic code is something that if you have a code word, if you were to shift all of this, if you have to shift this to the left and take this and put it on this side, then you get another code word. You shift these to the left and you move this to the other side and you get another code word. So cyclic codes became very interesting and very powerful. Powerful for those days. Convolutional codes is the other milestone. What is a convolutional code? It's nothing more than a shift register, a shift register, a shift register. This is the modulo 2 operation. And all you do is you insert binary digits into here and they come in and they fall out. They come in and they fall out. And whatever binary digits are inside here, an XOR operation occurs and you get a binary digit here. These two are picked and you get a binary digit here. And the code digits are picked off in this order. So for every one binary digit that enters, 2 are taken away. And this process continues. And that was a milestone way of thinking about error control coding. If you were to look at the state, if you were to look at the contents of these two shift registers, then you can see that there are only 4 possible states: 0, 0, 1, 0, 1, 1, and 0, 1. So this diagram is just a nice way of representing how this operates. So that, for example, if you're in the all 0 state, in other words, if that was a 0 and that was a 0, and you inserted a binary digit 1, then what would come out of here would be 1, 1, and you would move from this state to this state. If at this point you inserted a 0, you would move to this state. If you inserted a 1, you would move to this state, and this would be the corresponding code words. And this operation can be viewed as this as well. There's no difference between this diagram and this diagram. And in fact, this diagram is then collated into several replications. Now, I don't have the time to get into this thing, but this is the Viterbi algorithm. This is what Viterbi did. He basically concatenated this several times, and he placed the received sequence underneath. He used a very simple way to eliminate branches and ultimately choose the branch with the lowest metric and trace that back in order to output the corresponding sequence. We don't have time to get into this algorithm, but the encoding process is certainly easy, and the Viterbi algorithm is what you see it is. Okay. So block codes was one way of thinking about it. Convolutional codes was another way, and here is the breakthrough. The breakthrough was to use this type of a convolutional code, use 2 of them, use an encoder E1 and E2 in combination with an interleaver. So what's happening here is, this is the same thing. This is exactly this. What I'm trying to show you here is what happens when a binary digit enters. This is the initial state. The initial state of the encoder is A and B, and the final state is C and A. And if you were to work your way through this thing, you will find that C is the modulo 2 operation of A plus B plus U of K is the binary digit entering, and X of K is a systematic bit. Systematic because whatever comes in comes out, and this is the parity bit. These two would be given by this and this. Right? So if you were to follow this in your own time, you'll find that this is correct. Nothing difficult on the encoding part of it. So it's a very simple encoder which produces a systematic bit and a parity bit. The binary digits that you wish to encode enter this all the time, and they are then pushed through an interleaver so that you get an interleaved binary sequence. and they get encoded by E2. And E1 is the same as E2, exactly the same encoder. And again, this would be the systematic bit coming out and the corresponding parity bit. Now, what is very clever here is that instead of taking this bit, and this bit to create a rate 1/3 code, because 1 comes in and 3 would come out, what we do is we only take one of them. So this bit would come out and you'd take this particular bit. Then on the next binary digit, you would take this and you'd pick up this. So you're only picking, you only have 2 binary digits exiting at any given time for 1 coming in. So you created a rate half code. And there is the output. I've written it for you. So you get the systematic bit always coming through, but this parity bit picked up, and then the second one picked up, and then the first one picked up, and then the second one picked up. And that's the output sequence. The decoding is probably the most complicated decoder at that time, and it truly is the most complicated. Thereafter, it became a little simpler. This is the first map decoder. This is the map decoder. This is what was invented in 1974, and there's a second map decoder, and it is entirely based on probabilities. Now, if you wish to look at what those probabilities look like, then this is what they are. But what happens is essentially the Y's represent the bits that have come from the channel. They are then used to create this information. They are used to create these probabilities, which then produce L12, and they're interleaved, and they come into here, and they come into, and these are interleaved, and they come into here, and it is a very long, laborious process. There's a lot of mathematics behind it. The three French people who did this were mathematicians, and it was beautiful. If you do take the time to get into this, the mathematics is beautiful. It was based on log likelihood ratios, and it started a revolution into a mode of thinking that we need to start looking at log likelihood ratios. We need to start thinking about intrinsic information and extrinsic information. Extrinsic information is information passed from one decoder to the next. So you're constantly sharing information between the two, and you're iterative, continuing until you finally decide, okay, I'm going to decode the received code word. So this was, and it is the most complicated decoder that has been created, and it works beautifully. But it's very computer intensive. It's slow, and it can do the job, but it's slow because we moved on from this point. Let me give an indication of how powerful it is. So this is the simulation that I did where I had a binary source. It's a rate half. These are just, don't worry about this. This in fact is exactly this code here, exactly that. Going through a binary phase shifting modulator, AWGN channel, additive white Gaussian noise channel, a demodulator, and a turbo decoder. And the key thing here is that this is the probability of an error in a binary digit at this point here, right? That's what we're talking about, the probability of an error in a binary digit for a given amount of noise inside here. So if we go back to our slide, this is signal to noise ratio. This is the amount of energy we're willing to expend, and this is the probability of an error. And you can see that just by simply following this thing without iterating, after the first iteration, this is the performance. And as you iterate it, in other words, as you iterate between this one iteration, then another, then another, then another, and another, then what you find is that the performance gets better and better and better, up to the point where you no longer is there any need to iterate any further. And this very simple code, right? This is a very simple code, is able to beat the NASA K=7 rate half code that was used in Galileo. The Viterbi algorithm for the NASA code had an enormous amount of complexity because of the number of states, and performance was somewhere here, and this beats it hands down. And this is a very simple. I must stress, this is a very simple turbo decoder. So, and again, excuse my dog. It's 8 o'clock in the evening here. It's 8:30 in the evening here, so the dogs are a little awake. What about low density parity check codes? The breakthrough by Robert Gallagher, a PhD student in the 1960s. And they are a class of linear block codes. Just to repeat myself, the codes were essentially ignored because they were impractical to implement in those days, and they were rediscovered with the advent of turbo codes in 1993. I'll give you an example. If you look at this particular paper, he presented results where the probability of an error was like 1 times 10 to the minus 5, and it was like 0.13 dBs away from Shannon's capacity prediction. So to give you an indication of what I'm talking about here. I'm sorry, about here for the turbo code, just about here. Okay. So let's go back to where I was, which was slide 14. So they surpassed. Now this was the amazing thing. Turbo codes are no longer used. If you're looking for an application, you won't see turbo codes being used because they are very complex, unnecessarily complex. They are powerful, but with the advent, with the rediscovery of low density parity check codes, and now with the advent of polar codes, you have no need to go down to turbo codes. The low density parity check codes basically surpass turbo codes for numerous applications, and particularly where decoding complexity is a critical issue for high data rate applications. And this is the world that we live in. There are very few applications where we are looking for low data rates, where everybody's looking for information incredibly fast. So high data rates, turbo codes are just too slow and too over computer intensive. LDPC codes leapfrogged into the IEEE 802.16, .20, .30 standards, even into the 5G. So how does it work? Where is the magic? Well, I'll take the simplest low density parity check code that I could find. We begin with the parity check matrix. So this is created. How it's created, don't worry about that. But from the parity check matrix, we create the generator matrix. And the wonderful property of these two, as I stated before, is that if you multiply the generator matrix by the transpose of the parity check matrix, you get an all zero matrix. Now, it's very simple. You have the binary stream that you wish to encode, and you multiply this by the generator matrix, and out pops out the code word. We're back to block codes. We're back to the 1940s. And in this particular case, 1, 2, 3, 4, 5 came in, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 came out, a rate half code. If I was to represent these as code digits, right? These are my code digits, C0 to C9, and I multiplied by this. Then I could visualize that operation using what Tanner showed. This is what Tanner did, and it's called the Tanner graph in honor of his way of thinking. So if you take a look at the parity check code, then I've labeled the columns as C0 to C9, and I've labeled the rows as C0 to C4. Now, if I look at S0, you can see that S0 depends on C0, so it's connected. C1, you can see that C1, it depends on C2, so you can see a C2 here. Then you can see it depends on C5, and then on C6. So all the links between this node and all the code digits is represented by the ones inside here. And this is a syndrome bit, so that it's designed in a way that if this is a valid code word, if you've received it correctly, and C0, C1, C2, C5, C6, and C9 are received correctly, then this syndrome, this bit here will be 0 when you modulo, when you do an XOR operation, a modulo 2 operation between this, right? That's exactly what this is doing. If you were to do this, you would come up with the syndromes, which are nothing more than the modulo 2 operation of the bits specified by these ones and zeros. So for example, let's take S4. S4 depends on C0, C1, C3, C6, C7, C9. And if they were all correct, then this would be an all zero code word, all zero binary digit. Now, if I get a 0, a 0, a 0, a 0, and a 0, then I've got a valid code word according to all these nodes. And so the magic begins. What happens here is that an algorithm is used to try and scan across here and identify those code bits that are that show evidence probabilistically, provide evidence that they weren't affected that much by the noise, and therefore they need to be listened to. So that if you looked at this and you found that C0 and C2 and C1 were not really affected by noise, and there's a way of telling that, then you wouldn't want to listen to these bits. You wouldn't weigh them into your decoding algorithm as much, and in fact you would use these to correct these if possible. Now there's an intertwining. Can you see that C0 is influencing S0, S1, and S4? So there's a lot of exchange of information, and if you know that this bit is correctly received, then it heavily influences all these syndrome bits. It is a mathematical algorithm. It is wonderfully created. It's log likelihood ratio. A log likelihood ratio is saying that what is the probability that C of n is equal to 1 given the received vector. So given this particular received bits, I'm calling them R for 0 and C for the code word. So when C0 is sent, it is received as R0. This would be received as R1. It would be a floating point number. It wouldn't be a binary digit. This would be a floating point number. And the name of the game is to calculate this probability. There is an intrinsic information which is given by the code rate, the energy per binary digit, and a measure of the noise in the channel. This is the kind of mathematics involved, just to give you a flavor for it. This, in fact, is the algorithm. It iteratively, what it does is that it's using the log likelihood ratio to start with an initial estimate, and then it uses the extrinsic information provided by this side of the equation, where this is the type of mathematics involved. What it's doing is that it's improving its log likelihood ratio. This here, it's improving that on each of these bits as it iterates again and again and again and again. And it really is a beautiful set of mathematics which uses the LLRs, or log likelihood ratios, to iteratively improve your estimate of the received code word and therefore decode. Beautiful set of mathematics, and it works wonderfully. So by the time we reached LDPC codes, everybody was very happy, thought nothing can be done, nothing is better than this. And just when you are holding your breath, something else comes along. Let me just show you, just before I show you, the WiMAX IEEE 16 standard. This is the actual code that I implemented. This is the actual standard code. This is being used, and its performance, you can see, is very good. L max is the number of iterations you're allowing the decoder to iterate. So if you allow it to iterate 5 times only, then this is the kind of performance you'll get. But you get an improved performance where it gets better, but there's a point beyond which it's not worth it. And let's say 20 iterations. But for a WiMAX where you need fast decoding, 20 iterations is still not that much. Provided the communication between the user end-to-end is less than 30 milliseconds, the user will not be able to identify any delay in any phone conversations. These iterations happen very, very quickly. So 20 iterations within an LDPC code, within your cell phone, for example, is nothing. That's the WiMAX 802.E. And that's a simple code. That's the simplest, fastest code. And then as you increase these numbers, which are the size of the matrix, right? The matrix that I showed you was, what was it, 1, 2, 3, 5 by 10. This is the size of the matrix that you're looking at, and these numbers very quickly shoot up. If you wanted to move that curve down to here, you'd make that a lot bigger. You'd make those numbers a lot bigger. So polar codes, the newest kid on the block, the most powerful codes, and just when people thought that nothing is better than LDPC codes, along come polar codes, and fantastic, incredibly simplistic, and beautifully. They work absolutely beautiful. So if I take a look at a particular node, I'm going to call that R, I'm going to call that S, and I'm going to call that U. And the simplest way is just to show you. So U1 is a binary digit. That's a binary digit. And I'm looking at a very simple code in which N is 8 and K is 4. So in other words, I've got U1, U2, U3, U4, U5, U7, and 8. I'm going to set that to 0, set that to 0, set it to 0. Right? Very interesting. You're actually setting these to 0. And this is your message bit. That's your message bit. That's your message bit. And that's your message bit. So you're going to put inside here the binary digits, 1s and 0s that you want. And there's only 4, right? Like K equal to 4. There's only 4 entering. But you are presetting this to 0, this to 0, this to 0, this to 0. Now, if I take a look at a particular node, then it's just like this. And all that happens is that whatever this particular bit is, it's just replicated there. And R is nothing more than the XOR operation between S and U. So you take the XOR of S plus U, and that produces the value of R. And this U is just put inside here. So 2 bits enter and 2 bits exit. So if I look at this, if I look at this, then the first bit, which is R, the first bit is just U1 plus U2, and the second bit is U2. Nothing difficult at all. This is just a simple XOR operation. Here, this is U3 plus U4, and U4 is just replicated. And the same process happens at this side. What happens level above? Well, the same thing happens here. You take this, and you XOR all of them together, and then you take this, and you XOR those together, and then whatever is left on this side is replicated again. So these are just copy and paste. Same process happens on this side. Ultimately, you end up with a code word which has got 8 bits, right? And this is a rate half, a very simple polar code. How does it decode? Beautiful. If I was to send X1 to X8 and I call the received bits as R1 to R8, and these are numbers, these are sent using binary phase shift keying. There'll be floating point numbers depending on what was sent. Then what happens is that you in any given node, you use a function f. I won't get into the mathematics of that, but you use a function which allows you to send information down from the parent to its left child. And once you have made a decision on that left child, the decision that you made, which is then used, this S is then used, and it is used to decide what happens on the right-hand side. Now, let's try and follow this. So, for example, let's look at L41. So, for example, L41. L41 depends on L31, and you can just see over here. L41 depends on L31 and L2. So whatever happens between this node and this node is used to determine what is L41. Now, L41 happens to be a forced binary digit 0. So you end up going through the decoder. I'll show you in a second how I got down here. But you use the fact that this must be a 0 in order to traverse back up the tree. You come down this tree and you know that this is a 0, and you're using that very fact that it's 0 in order to improve your ability to correct any error whatsoever on this particular bit. Right? So you use the fact that you know what the answers are, and you use this extrinsic information coming down here, and you know what the answers are, but you still go through and you use all of that information to correct this. Then, armed with the armory, you come down here, and once again, the process repeats. You know this, and you can find this. But these actually affect these as well. So probably a nice way of looking at it, this actually is the decoding algorithm. You use L15 and L11 to find out what this is. These two determine this, these two determine that, these two determine that. It's written right here, so that, for example, L2J is depends on these two log likelihood ratios. These are all log likelihood ratios, and you're coming down the layers using this particular algorithm all the way up to the what is called the frozen symbol. That's a frozen symbol. Once you have found L41, you then use the G function, another function, to determine what is U2, which is what happens to be a frozen symbol in this case. But you use L31, you use L32, and you use your decoded U1 in order to decode this. So in other words, you come down the tree, and then finally you make a decision on that, but you know the answer, but you make a decision on that, and then you use that correct decision in combination with these two to determine this bit. That is how it continues. If it's confusing, I'm sorry. I don't have enough time. We're already at 10 to 9 already in the evening. So I want to come towards the end of this. But I'm hoping I'm making sense. The encoding process is ridiculously simple, and the decoding, if you take a little bit of time, is actually very beautiful, and it is nowhere near the complexity of low density parity check codes, or most certainly turbo codes, and they immediately were brought into the 5G standards. So where are we now? Well, even though, let me just flip back to this curve here, even though we could be operating in this region with error control coding, we stick to rate half codes. We're down here where we need a little bit more bandwidth. But Shannon is saying that there are codes available with very, very low bandwidth requirements and still achieving error-free communication. And so what I'm trying to say here in this last slide here is that for standards, which include synchronization, error control codes have found themselves becoming rate half, rate three quarters. And what we do is we switch between the different rates of rate half and three quarters on the fly. They've become standardized, and you're able to use the same piece of equipment in various parts of the world. So even though we could be operating in the upper regions of the Shannon's promise, we typically end up at the rate half level. That doesn't mean that we won't end up using more bandwidth efficient, high performance error control codes, but for now we're high bandwidth but very powerful codes. So we're sitting at the lower end of the Shannon's curve. Polar codes can achieve near capacity using rate half codes, and given the processing power now available, we can most certainly expect these codes to spread into other applications. It should be noted that even though that kind of power is available, concatenated coding is well established, and even though not as powerful, the potential gain may not be worth the extra expense until chips are mass produced. So for example, the error control coding mechanism used on your SIM card, on your SSD cards, will not be polar codes. That's an overkill. The number of errors that happens within that, a simple block code, Reed-Solomon code, convolutional code, or whatever, is more than enough. So it's not that just because we have polar codes, there will be every single application of error control coding will be polar codes. It's only when you need that level of power that you would resort to polar codes. 60 years of error control coding has produced a barrage of codes, and they all have their applications and their expense. So you would use error control coding accordingly. So where do we go? Where do we go from here? Well, the combined use of coding and modulation at a higher code rate to achieve capacity, limited by only our imagination, is the future that I see. I developed target codes, which combines coding and modulation in collaboration with Professor Moon at the Utah State University. And the idea is that you now no longer need, you no longer live within, the constraints of shift registers and shift registers like this. You basically dismiss those. You don't need them. And if you look at my paper on target codes, you will find that we just use the modulation, just the module. This is the signal constellation of the modulator to create an error control code. And the magic is that, again, you're not limited by XOR operations. It's not limited by any form of mathematics. It's just by your imagination. Okay, that ends the presentation. If you wish to look at my CV, just type in CV and my first name, last name. And if you wish to look at the book that I created a few years ago, it's fully multimedia. It has about 300 odd MATLAB and MathCAD simulations, which simulate every aspect of the theory presented in the book. Then you can take a look at sample information inside here. Okay, and that concludes my presentation. So I will now stop sharing.
We thank you very much for your time and presentation. It was a great presentation.
Thank you very much.
Puerto Rico and Caribbean section members, thank you for your support. They also thank you for your time. And of course, we are giving the members the opportunity to know more about error control codes. Also, we encourage our members to remember that the elevation for senior membership, we are at your service. And of course, Dr. Janak Sodha is one of our recent elevated members. It's a pleasure for me, as I was a reference for you. And as you may know, I'm at your service too. Thank you for this opportunity and also for your time once again.
Thank you again for inviting me. Wonderful. I hope it was useful.
Thank you very much and have a good night. Thank you.
Bye-bye.
Bye-bye.